into scaling, and it starts with this, with this thing where he says that he has been interviewed, many times about different topics, but this time, this particular interview was about Godzilla because it was some kind of new movie. I didn't watch that movie. I think I know what he's talking about. Uh, was it about King Kong versus Godzilla, something like that? Something that came out a few years ago.
Yeah, and another one, Godzilla One Plus or something. Or yeah, just came out. That was
Yeah,
really good.
and it's great because, of course, our imagination, whatever leads us, this is why we have entertaining things. They don't have to be all the time scientific. The problem with being a scientist is that I watch many times, sometimes some of these movies, and I like what is called hard science fiction. That means, like science fiction that is actually based on science and not just fiction. Because one thing is to have fantasy, and one thing is to have science fiction. But I guess there are some science fiction authors that are actually scientists. They write stuff, and you can use imagination, etc. But they try to do as much as they can to stick to the science, with, of course, going beyond what is known right now, but in a very plausible way. And then there are things that are completely made up, and they don't have any scientific basis. And then some of the scientific movies that sometimes I watch, like I cannot even watch them because they are so bad. Like something like this is fun because the premise is so absurd that it doesn't even make any sense anymore. You just enjoy the action, and you let your imagination run. But there are other movies where I cannot just stand it because they pretend to make like scientific arguments, and then it's completely ridiculous. But anyway, so he was mentioning how they come to him and ask, didn't even think, the journalist didn't even think that it was questionable, the entire idea was questionable to have such animals, such beings so big, um, and uh, um, and just wanted to know what will be the characteristics of such an animal, like how strong it will be, how fast it will be, etc. And he dismissed it completely, saying, no, you could not even have such an animal. It's impossible. And this is why, because people in general are very bad and this is why this is so relevant for Bitcoin, because if what we are saying, if all the science we're developing about Bitcoin is correct, and it seems that is correct, there is everything that supports this understanding of Bitcoin, scaling is fundamental, right? The fact that it went from being a small little fraction of a dollar to almost 100,000, and one day will be 1 million, maybe even 10 million. It's all a story about scaling. And he did it in this regular fashion that we are mentioning all the time through these power laws. That means it's scaled up, it has scaling properties. So this is why it's so relevant for Bitcoin. We're not just talking about things that are not related, because after all of us are united here because we are interested in Bitcoin. And so it's very important to start to train yourself to think about scaling as like a fundamental property. Uh, and uh, um, and so this book is amazing because it's all focused on scaling from many points of view. But this chapter, it's so fundamental that it needs to be discussed. In fact, we can stay on this chapter for a little while. Maybe even next time we can review and maybe come up with different examples, etc. So other people join, we can have a larger discussion. But so this is a very cool example because it's fun. First of all, right? Almost everybody has read some book where there are giants, where there are big animals like that, and we maybe imagine, like fantasize what will happen if we encounter such a being, etc. But it's very important to start to think, because one thing is having fun and be entertaining. The other thing is investing, right? And so if you want to invest in Bitcoin, you want to understand it. You also it's not just about the money, but you also want to understand the technology. You want to understand scaling. And so the book then goes and starts to let me click on the slide. Uh, okay, and you see this. Oh, we are not. I'm not sharing the slides. Okay, I have slides.
Yeah, slide sharing is a little tricky, but uh, you've done it before.
Yeah, I thought I did, and I had like a nice little picture of Godzilla. Okay, and you can see it, right?
Yep, yep.
Perfect. So yeah, the previous slide that I had was this one, with I don't know, two friends, and some people root for one or the other. I don't know which one. I think I like the lizard better. Uh, anyway, and then the chapter starts to talk about Galileo, and this is so cool. First of all, okay, Galileo, it's my countryman, right? It's Italian. I love him. Um, and he is also considered the father of science. He's considered because, of course, it's not that there was no science before Galileo. There was. It's just that he really is really formalized science in a much more rigorous way. He started to, and it was a very difficult thing. People don't realize because, and of course, once in a while I joke, and say I'm like Galileo because I'm fighting all these other people with all these different ideas about Bitcoin, these antiquated ideas that we can think about it like if it was a financial asset instead of science uh, or physics. But of course, there is no comparison, right? It's first of all, he was like trying to discuss about the universe. We're talking about Bitcoin, but we can take seriously, but it's still not like trying to understand the entire universe. Plus, the times were different, of course. Like yeah, it's a joke more than anything else. But there are some little bit of parallels there. But you had to fight the culture of the time because at that time people don't realize it. It was almost like the Taliban's. It was really that fanatic. European people, took very, very seriously religious arguments. You didn't have much freedom. You could be jailed or even be killed if you were going against the thought of the time. And the church had their own state in Italy, like 30% of Italy was actually a country run by the Pope, but the Pope also had a lot of power on all the neighboring countries or states because Italy was breaking down, and not just Italy, but in they were at that time they were starting to discover America, so there were like these Mexican colonies, and so they had a lot of influence. This church had a lot of power and a lot of influence. So directly or indirectly, they could ask somebody to be arrested and then brought to Rome, or somebody like the Inquisition, right? They had this thing called the Inquisition. They could go there in that country and prosecute somebody for their ideas, And just before Galileo, there was this other thinker. His name is Giordano Bruno. I don't know if you ever heard about it, but he was more like a philosopher than a real scientist. But he started people started to think about these things because it was in the air, right? People started to um, leave this idea from the ancient times and kind of start to think for themselves, to start to look at nature in a different ways. This was called the Renaissance. This period it was called the Renaissance because it was a renaissance in human thinking, human economy, the way people. This is when actually the banks were created. In the beginning, were actually kind of useful. They were mostly like exchanging coins. Like you will come to a country, you want to do commerce, and you had coins from your country, and you could exchange them. for the coins for that country. Banks were invented in Italy too. Um, the word bank comes from desk. It's like a little desk. We had like a little desk where these money changers were exchanging the coins. So there was a lot of new things happening, and this new way of thinking about reality. And this guy, this philosopher that came before Galileo, he heard about these Copernican ideas where we're starting to talk about how the Earth is not anymore of a center, but the Sun is a center of a solar system. And so that was really revolutionary. We cannot imagine right now how incredible that was, because for centuries and centuries, it's not that people didn't think that the Earth was round. They did. That was not a big revolution. They knew that the Earth was round. Like, probably people in the Bronze Age or even before that thought that Earth was flat. But uh, in the classical times, people, and even during the Middle Ages, people knew the Earth was round. Maybe some ignoramus on some mountain or something. They didn't know, but most people knew. Also because they could see the mast of a sail. If you live nearby the sea, you could see it. You could see first the mast of the ship, and then the rest of the ship, and finally the entire ship. They knew it was around. But the problem is, they thought that the Earth didn't rotate. They thought that everything rotated around the Earth. They thought that it was the center of the universe. Also, they thought that whatever physics happened on the Earth was very different from the physics that happened everywhere else. That the universe, like if we went beyond the atmosphere, and we had some sense of the atmosphere, being like this layer of air around the Earth, then the world behaved in a very different way. They had like laws for the stuff on Earth and laws for the stuff in the sky. And instead, if you put it the sun at the center, then the Earth all of a sudden becomes like another planet, like everything else. So there is no difference between heaven and Earth. That was really revolutionary for many people. And then the idea that you cannot completely trust common sense. You have to kind of study and understand and go deeper. That again, it's very relevant for Bitcoin. Um, and like you cannot just jump on what it looks like. You can still trust your senses, but you have to be careful in what the senses tell you. So, for example, it looks like we are static. We are not rotating around ourselves. Around the Earth is not rotating around itself, or it's not going around the sun. But that is the case, and there are reasons why it doesn't feel like that. You can go through these reasons. And so Giordano Bruno made this jump of imagination and thinking, and he said, well, if that is true, that the sun then is at the center of our local place, what now we call the solar system, then all these little dots that we see in the sky that we call stars, maybe they are like the sun. They look small because they are far away. I mean, that was a really big thinking for that time, right? Big thinking. And so he say, they are nothing else than suns. They are like some of them are going to be bigger, some of them are going to be smaller, but they are all little suns. Like not little suns, they are suns. And so maybe around these suns, very far away, there are planets like us. And in some of these planets, maybe there are people. Maybe weird people that look very different from us, but there are people. But this was amazing, like what he was thinking. And it was not the only reason. He had also, he basically didn't. He was a priest actually, initially a monk, and then he kind of started to leave the church behind. He started to have all these other interests. So it was not the only reason. But he kind of started to say with other type of thinking, from the ancient times, like the Egyptians, etc. Everybody had different ways of thinking about the universe and life, and there was some knowledge about. Hi, Karuga, nice that you join us. And so there were more than one reason, but one main reason was that, this idea that there were people around. Because then, if you think of it religiously, are they also, do they know about Jesus? Because these were very important questions for them at that time, right? Uh, these aliens, do they know about Jesus? Did Jesus, like an alien Jesus, died for these people, in that planet, So can you imagine it was like a kind of worm that he opened, and the church didn't want to deal with that, so they arrested him, they tortured him, all kind of horrible things. And then, because he refused, because he was very coherent with his way of thinking, they burned him to death. And so Galileo was very concerned about that, but he was also a man of science, and he stick with his thinking. And but in the end, he was arrested too, and basically they kind of told him more or less directly, if you don't want to end like Giordano Bruno, just reject your ideas. And so he had to reject his ideas. He was put under house arrest. He could write about anything else that was not astronomy, because that was the thing that the church didn't like. So, when he was under arrest, house arrest, he wrote this book where basically he had two people, a group of people discussing ideas. And he called it dialogue over the two maximum system of two great systems of the world, right? So the English version, I have it here. Let's click it on it. Uh, yeah, so uh, let me shift. Dialogue concern with two chief world systems. Kind of crazy title. He didn't call it like that. They forced him to write it in that way, mostly because they say, okay, but you can kind of write about this stuff if you propose it, like if you give equal opportunity to both systems. And so you have somebody representing one system and somebody representing the other system, and they discuss, they debate, and then the reader can kind of make his mind. It was pretty, because the church was bad, but not extremely bad. They still kind of accepted the people thinking a little bit, etc. They were, it was politics. It was a lot of politics. But then he kind of exaggerated where he made the guy that was supporting the Copernican, the geocentric system, like a little stupid guy. In fact, his name is Simplicio, that means like simpleton, simple guy. And the other one was like a dead friend of Galileo, that was like a scholar and a philosopher, but he was dead, so they couldn't go after him. So it was a clever way of finding somebody that could take it, because he was dead. And then there was like an arbiter, like a kind of moderator in the middle, that was allowing the two approaches, and you can see in the graph, probably the Simplicio guy is the bald guy here. See this drawing from like probably an original book. These books, by the way, they cost like a lot of money if you can find like an original book from that time. This was written in 1630, something like that. And the guy, the one that supports the heliocentric system, it looks like some kind of philosopher, like professor, some university. Like he has a nice fancy hat. He has some kind of astronomical instrument in his hands. And then there is a guy in the middle that probably some kind of merchant, some kind of practical guy, and it is being like the moderator, of this debate. And they debate all kind of things, but the main goal of the debate is actually trying to prove that the Earth is at the center, that the sun is at the center, that the Earth rotates, and we had all kind of objections. Some of them okay, but other kind of silly, like oh, what if a bird flies and the Earth rotates? Will not the bird smack against? So funny. Will not bird smack against the tree? So we had arguments like that, and little by little, the guy that represents heliocentric system kills it, kills all these bad arguments. But among the others, there are other things that he discusses. He discusses things that not necessarily are related to this topic of the Earth being rotating around the sun, going around the sun, but kind of general way of thinking about life and the universe based on reasoning, based on math, because he started to introduce this idea that math is a language of nature, and people were not used to think about these kind of things. People kind of they knew about geometry, and geometry was a big deal, but it was mostly like used on things like land. That if you had to establish how big a land somebody owned and things like that, but they didn't use it like to do maybe in some commercial applications, like practical people. Now in construction, they knew how to build boats, and in fact, actually, this is one of the things that they say Galileo was very influenced. We had Florence, where he, or the other city where he lived, Pisa, for example, all in this region of Italy called Tuscany. Then he went to Venice. But people in Italy were building all these beautiful boats, and some of them, they knew, like the Spanish people had these almost like spaceships, the equivalent of spaceship at that time, that we were using to go to America. The technology was amazing, So from a practical point of view, they didn't know the physics maybe, but they knew how to build things because by doing it, they learn. Same thing with the Romans. They didn't have the physics and the theory, but they knew that if you do this and you do this other, then the bridge will not fall. You need to put a capstone. They had a lot of practical knowledge about doing things with your hands, and like mental models in their head about how the word used. But Galileo started to teach people that we can use math. You can use math to make inference about the word. And it's interesting that one of the arguments that he has in the book, it's that it's not necessarily related to these things, like I was saying, about talking about the Earth going around the sun, because they cover many different things. They're trying to understand the motion in this book because it was a big deal. The understanding of motion at that time was all based on this ancient understanding of motion. It was all wrong. Why objects fall down of the earth. They had some explanation, but it was like all silly explanation. Maybe on a certain point we can go through it because it's interesting. But what is mentioned in the book, because it's all focused on scale, is this thing that this passage, and he's talking about here. So reading it. You can plainly see that the possibility of increasing the size of structure. So they already had some discussion going, but then this is the conclusion from Salviati. Salviati is the clever guy, is the heliocentric guy, and he says, for what has already been demonstrated, you can plainly see between possibility of increasing the size of structure to vast dimensions, either in art or in nature. Like art here, what art here is meant is basically things made, what we will call technology. It's, basically things that people do, like buildings and things like that. Likewise, the impossibility of building ships, palaces, temples of enormous size in such a way that their oars. Hello, Moto. Sorry. In such a way that their oars, yards, beams, all the parts will hold together, nor can nature produce trees of extraordinary size because the branches will break down under their own weights. So it will be impossible to build up the bony structure of men, horses, because actually people were taking seriously giants, right? So they were these mythological ideas, but and now we say it's mythology. At that time, they really believe there was a time when giants went around the earth, and there are people even now, because they don't know science, or they read these tabloids, and they think that they were ancient times. So they look at these aliens, these ancient aliens documentaries, and they believe they were giants. But it's amazing that at that time, hundreds of years ago, Galileo, using his logic, using his mind, trying to think differently from everybody else, is using very simple arguments and some basic math to come up with his understanding. Okay, and so what is based on what? So he has these arguments, right? So this was the conclusion, but what he was talking about, and so these are some of the things that I already mentioned before. If you have heard me about talking about this topic, is that as we scale things, so what scaling means? Scaling means you make things bigger or smaller, right? And not by a little bit, by a lot. So if you ask a question, okay, I have this thing, like with Godzilla, I have like a lizard. Now I take this lizard and I make it 10 times bigger, 100 times bigger, 1,000, in case of Godzilla, if we, even if it, I know that we were dinosaurs, but there were some reasons also why we had dinosaurs in a certain time of a world history, of the Earth history, and not now. And we can go through them through. But you also, if you go and look at the bones of the dinosaur, they were very different from mammals, because they were so big. And and so there are reasons why things happen anyway. But so if you take a mammal, or if you take like King Kong, or if you take a lizard and use like a normal lizard right now, or like even a relatively big lizard, um, like some of these whatever, well, how they are called. So you know what I'm talking about. I don't know. It doesn't come to my mind. Some of these huge big lizards, that iguanas, like an iguana, right? You take an iguana and you make it, I don't know, 100 times bigger, a million times bigger. I don't know how many times bigger you have to make it to get the Godzilla. Let's see if it is, say it's tall 100 meters, and so 100, at least 100 times, and a big iguana is like less than a meter. So we're talking about maybe 1,000 times, 1,000 times bigger. What will happen, to everything, to its weight, to its the structure of their bones, and the argument that he used was relatively simple. Okay, and you can go more in details, but this is how we like in physics or in science, is to make these kind of rough estimates. You don't have to do very complicated calculation. You can always do something very simple like this first. And I would like everybody to train themselves with this, because it's really cool. You start to see the world in a completely different way, and these type of calculations are called back of an envelope calculations. And my countryman, not just Galileo, but also another physicist, Italian physicist, his name is Fermi. He was a genius in doing this kind of calculation. There is this famous episode where we were testing the atomic bomb here in New Mexico, before launching it on Hiroshima and Nagasaki. It was a test, right? Um, they did this experiment in the desert, not kill anybody, and in fact, but they put a lot of soldiers around. They got radiation. Many of them died of cancer later. But they were far enough, but they got a lot of radiation because they didn't know anything. They didn't know. There was some scientists, they even thought of it. There was a small chance that the entire Earth will burn, and they still did the experiment. But there were some crazy arguments about it will be like a chain reaction, and then the entire Earth will burn. But most scientists, they didn't think that was the case. But they didn't know anything. They didn't know how big the explosion was going to be, how powerful, etc. And so they added, sensors, of course, whatever they had at that time to measure these kind of things. You could calculate the power of the bomb by measuring the light, but also measuring the wind, that is produced, blast. And so they had all kind of instruments all around the bomb. But and plus, and Fermi was involved because when he got the Nobel Prize, we gave him the Nobel Prize for physics for his research. His wife was Jewish, and so he left Italy because it was fascist. He already didn't like fascists. Plus, his wife was Jewish. He knew what was going to happen eventually, And so when he got the Nobel Prize, he went to Sweden, got the Nobel Prize, and then they left for America. They already probably had some contacts or whatever. And America, of course, wanted him because he was like a genius, and he was working in a very important topic, that they knew was a security issue. So they got, he went to Chicago. He started to teach there, and he built there like a basically atomic pie that was like an equivalent of basically a nuclear reactor, but instead of exploding it, you make it go slower, like it's under control. So instead of releasing the energy all of a sudden, it does it over time. And but it's the basic of understanding also atomic bombs work. So when we did this project in Los Alamos, where we basically kind of put all these scientists together, lock them up, and say, now build us an atomic bomb. I think they should do things like that every time there is like a serious problem for mankind. We should take a bunch of scientists. Hey, we give you food, nice salary, solve us this problem. Put all the resources we can. You solve us this problem. You came out. We give you pizza. Come out when you solve the problem. Whatever we are struggling with, that is the top of our priority. But they don't do any more things like that. But we did it for the war because it was like a matter of life and death. We were afraid the Germans were developing their atomic bomb. It was one of the things at that time. But he was there. He was like one of the main contributors in creating this bomb. He was not the only one, but we had a lot of other Europeans that were escaping from Germany and the craziness. So we had most of them Jewish or related to Jewish people. Maybe their wives were Jewish, like with Fermi, and they were trying. They were contributing in building this weapon that hopefully was going to end the war, and maybe was not going to have any more wars, right? So because of that weapon, that kind of turned out true because we have wars, but small ones. In comparison with huge big world war. So it's horrible, but at the same time maybe that was needed not to have any other world war. And so when they exploded the bomb, they had all these devices around it, and so you could collect data. But he was so curious that he wanted to know when they exploded. So they had this kind of bunker very far away for all the scientists to observe it, all the technical people, to see what happened and understand the phenomena, visually, not just with cameras or other things like that. And he actually was crazy and brave, and he went out of the bunker, and he was far enough where there was a blast, but it was relatively small, so it was not super dangerous. Probably there was a radiation. In fact, eventually he died of cancer for a reason. Like many other scientists, they were playing with nuclear materials and radioactive stuff. They didn't have all the safety that we have right now. But he dropped these little pieces of paper, and by the deviation of the papers, he was able to calculate in his head roughly the power of a bomb. And he was not far off. I think he was off by a factor of maybe 2 or 3 or something like that. But when we talk about the order of magnitude, you understand he got it right, because when you're thinking about order of magnitude, is this bomb, this power, 10 times bigger, 100 times bigger. So you care only by factor of 10. This is called an order of magnitude argument. And it's rough, but it still makes you understand, right? So when we say when Bitcoin goes, it would take 10 years to go up a factor of 10, that is exactly a kind of order. It's more precise, right? Because we have a formula, it's more precise than that. But it's roughly at its core an order of magnitude argument, because we see how Bitcoin scale over time. It seemed that it did this scaling in a very regular fashion. And then we say, if it continues to behave in this way, and usually systems that have this scaling property, they do, because there is something fundamental about the system that makes them behave in that way, then it will take another 10, because basically you're scaling up both the price and the time together. And so this is how he was able to calculate the bond power through these scaling arguments, through this in his head. He did all in his head. This is how clever this guy was. And Galileo started it all. In fact, in a certain sense, science started from reasoning like this, thinking about nature using math and very simple scaling arguments. So here there is this picture that Galileo was using, and he was saying, listen, if I'm making an animal bigger, his mass is going to scale up. His mass is going to scale up, his size is going to scale up, and he's going to do it with the volume, right? So with volume, everybody's familiar what volume is basically three-dimensional, right? Because we go X, Y, and Z, right? So we need to scale up in all these three dimensions, roughly, right? And in physics, we sometimes make fun of us because, okay, we use a spherical cow, right? When we think about cows, we think, okay, we say, approximate the cow like if it was a sphere, or approximate the cow like if it was a cube, right? So this is why we have a cube here. It's a rough approximation. It's funny for some people that are not used to this kind of things, but it's good, right? If you're trying to do a order of estimate, if you're trying to order a magnitude estimate, it's okay. And the cube is simple to calculate. Now, after you can go and try to kind of capture the shape of whatever you're discussing, but you will not be off by a lot, right? Maybe a small, a small factor. The big idea is still there, and you can simplify by using these cubes or spheres, because it's easy to calculate in that way. So the idea is that if you are squaring something, I mean, you're sizing something, you're doubling the size of something that is cubic, right, that is three-dimensional, then you go up with the cube. So if you double, and that means 2, right, you know already that the volume of that thing that you're doubling is going by the 2, right, the factor that you're multiplying the object by, raise, right, that power that comes so much often when we talk about power laws, etc. This is why we call it the power of 3. And so the simple math, right, what power of 3 means. You multiply 3 times. That's what that power means. You multiply 3 times, right? 2 times 2 times 2. That is 8, right? 2 times 4. 2 times 2, 4. 4 times 2, 8. So 2 to the 8 means 8. 2 to the 3 means 8. So the volume goes up with 8. Because mass, it's nothing else than the density of the object. So if the density stays the same, kind of, right? If it is made of the same stuff that it was made before, this thing is going to have 8 times the mass. What about the other relevant things? Well, you say, well, you will have this big, huge mass for this big animal. This is what Galileo was saying. Oh, it can be a house, it can be a temple, it can be a ship, whatever you want. And now it needs to sit down, right? It needs to have contact with the ground. And that contact, because it's a surface, it's a square. It's like a square, right? It makes sense. You see how you reason about these kind of things? You think, say, okay, what are the relevant parameters of the mass of the object and the surface? Why the surface? Because the animal needs to stand or needs to walk, or the sheep, even if it is a sheep. With the sheep, probably it's better because some of it is under the water, etc. There is more support from the water. The weight is distributed. This is why, you can have these huge, big sheep, and they exist, right? But it's a different thing, right? When you go to the sheep, you discuss something in a different domain. But if you're talking about an animal on earth, on the ground, then this animal needs to walk, right? It's going to have feet. The feet are surface, right, where you put your feet. And in fact, even worse, right, because usually the feet are a small little portion of the animal. It's not like, literally a cube, like a giant cube with movie like Godzilla is not a cube. So it's going to have some little feet that represent a small component, but again, to simplify, we think that, okay, what if the animal, the total surface that he can have is wherever one of these sides are, because, it's going to be worse, right? So let's try to kind of steel man this argument and see if it still holds. So let's look at the best case scenario. So in that case, will be the entire surface of that cube, but I mean, not the entire, because just one of the sides, right? Because it needs to sit on the ground. So the volume went up with the cube because we are talking about an area. We know what an area is the square, right? So instead of the power, right now, for the surface, for that little surface that is in contact with the ground, is going to be the square. And so if I double the size proportionally, now every side, right, every side of this cube, now the power is 2, the relevant power is 2. So the area goes up with the square. And so what is next in the thinking is, well, what happens to the pressure that the big mass exercise on that little area? Because pressure is mass, right? The mass, the weight of the object over an area is what pressure means, right? So when you walk and your feet are tired, is because you put all this pressure on your feet. And it's not just a question of getting tired, but also the weight that the bones, because right, the way that actually it's not just a cube, right? The animal has bones inside it, and these bones is what they carry the weight, what the weight is distributed over these bones, right? Same thing with a tree, etc. So he was thinking how much force over area, that is the relevant quantity there is. And you can see that because the mass goes up with the cube and the area goes up with the square, as we make this thing bigger and bigger, you have to take the ratio between the mass and the area, and one goes up with the cube, the other one goes up with the square. If you take a ratio of these two, everything, right, the pressure, the relevant quantity, that is the ratio between these two things, goes up with linearly, right, with the size of the object. So by the time you go up by a factor of 1,000, so if you want to make a lizard, an iguana 1,000 times bigger, 10,000 times bigger, whatever the size of Godzilla is, you're going to get 10,000 the pressure. The only way to handle that for something like a bone or organic is, to have some kind of crazy material, that doesn't exist, that will be able, to handle that kind of pressure, or making the size of the bone much, much larger, like in area, now they can distribute the weight. So the Godzilla for sure will not look like it looks right now. It will look like something completely weird, like with huge, big, enormous feet, and probably at a certain point there is even a limit to what they can do, because we know of an animal, right? We know of an example where that happened exactly, right? So for example, the elephant, where yes, it tried to be bigger for a different reason, because there is a big advantage in being big, because then in particular if you're for example an herbivore, and you want just to eat all the time, and there are these, like, that you can see in the background, these nice cats, they want to eat you. So being bigger and bigger helps you, because then they don't bother with you, because even if you don't have their sharp teeth and fangs, you can charge them and kill them. Size matter, but you have to pay a price, and the price is exactly that. So first of all, notice how elephants have these huge big legs, right? There is a reason why they have these enormous feet, like they look funny to us, like they almost like look like some trunks of a tree, because they need to distribute the weight, and that is probably the limit of what is possible. So they kind of resolve the problem, through evolution or whatever other mechanism. Elephant didn't go to a drawing room and say, let's make my feet bigger. They did it little by little through the evolution process. But there is a reason why there are no animals, at least mammals, at least right now. People mention every time, what about the dinosaur? First of all, with the dinosaur, they it looks like the atmosphere was different. We had more oxygen available. So that doesn't solve the problem of sizing, but it solves other problems like metabolism, etc. But again, probably dinosaurs are the limit of a limit of a limit. And even there, if you look at some of these brontosaurus, etc., they have legs that look like literally trunks. And probably that is really historically the limit of what you could have. And they were big, maybe like a house, like a small little house at most, and maybe there are, I don't remember what is the record, etc. But there is nothing that it looks like Godzilla, we never had anything like that. Godzilla is big as a skyscraper, that is impossible. So there are reasons why these things don't happen. And then you have other issues. It's not just a question of sizing the legs and the bones, but also dealing with metabolism, dealing with the heat, because you're producing all this heat. Again, the heat will be proportional to the how much cells you have. How much cells you have go up with the mass of the object, and so you're producing more heat, right? Now we know that before, because there is another power law that is not directly proportional to the mass of the object. Metabolism, actually, there is some kind of scaling uh, uh, principle there too that we can also talk about. And we already talked many times, but we can talk again about it. But again, it's kind of close to linear, not perfectly, but again, you will have a problem because the surface of the animal that dissipates the heat goes up with the square because it's a surface. And so here you have a problem where you're producing all this heat and you have to get it out of your body because of, otherwise you cook inside if you are not able to dump the heat outside. Again, things that normal people don't think. Scientists think about all the time about this thing. To me, it's natural to think about this stuff. I'm thinking about this stuff all the time. Unless you're trained, you don't think about this stuff. But so this is why the elephants have these big, huge ears, as you can see. It's a cooling mechanism for them. So they increase the area of their body, and now they have a lot of veins, a lot of vessels, and they can, and then you can see them. They can move them around, to move air around them, etc. It's basically a ventilation system. I know it sounds weird, but this is what it is. And so there are a lot of things like these that happen because of this scaling property. And when you start to understand them, you start to understand the world around you. A lot of different things now they become interesting. And so this also, like I say many times, we want, because scaling seems to be so important with Bitcoin. If you're a Bitcoiner, you want to understand scaling. It's a very, very important topic. Okay, so I talk about an hour. The chapter is now over, and there are so many other things to explore, and they're interesting. But I think this is a good introduction. And then, hopefully next Thursday, more people will join, and we can continue the discussion. But I want to spend, maybe 2 minutes, 5 minutes for any questions or discussion. So do you have any question?
Yeah, I was thinking about like the pyramids and like how pyramids grow. It seem like they can get super large, and then you think about
Mhm.
mountains, and they're kind of shaped like pyramids. And I wonder
Yep.
if the way they're designed, maybe the Egyptians knew this ahead of time, or is there a limit to how high a pyramid could get, or the
Yeah,
tallest thing
and
in the
let me
world's a
ask you,
mountain?
let's reason.
But by
Okay,
the
I'm not trying to put you
uh,
on the spot, but let's reason through heat because, first of all, your intuition is amazing, very good. Pyramid is a perfect example of how you think about stuff that you never thought about before, and now you have this scaling window that is opening, and now you're starting to think about stuff. You say, oh, whoa, maybe there is some scaling argument there. What do you think is going on with the pyramid? Why is relevant? And why it has the shape it has. What is going on there? What do you think?
well, it obviously doesn't. As you increase the size of the pyramid, it doesn't go up by the cube, and I don't know exactly. it's less than the cube, but the surface area of the base is
Yeah,
getting
I mean, the mass
larger.
still goes up
So
kind of
I don't know
like
if
the
it's a one-to-one
cube, right?
relationship.
Because it's still three-dimensional, but differently from the square. Now it starts big at the bottom and it goes smaller at the top, right? This is what the definition of a pyramid is. And so it's
Yeah,
actually better than a cube because as you grow, this mass will still kind of go with the cube, but now because it's so extreme in how it's built, even if roughly goes up with the cube, because there is a little bit of saving grace there because it has, you start to have smaller um, components that go up relatively to how much you have of a base. Okay, and in fact, one could write an equation to express that, etc. But that is the intuition: is that it's if you want to build something big, monumental like that, making it shaped in that pyramid fashion, it's a very good idea. It's probably the best type of shape, right, that you can have. Um, and then you're saying, okay, were the Egyptian knowledgeable of it? Well, first of all, there is, in the way that the Romans were knowledgeable about building things that stand right now, hundreds of thousands of years later, but if you go in Italy, you see all these ancient bridges that were built by the Romans. How come they still stand 2,000 years? Because they discovered some of these principles, but they didn't have a science of it. It was mostly trial and error. They tried different things, they failed, they collapsed, and then they tried another thing. And if you try enough, and you are, you know, there are a lot of people that are geniuses about building things. And take a carpenter and maybe doesn't know the physics of a door, but they did it so many times and he has experience with it. That he's a genius about doors. How to build them. And make them strong, etc. That he has to put this 4x4 here and 2x4 here. And so by doing things you learn, right? And so there is evidence actually that the Egyptian had tried many smaller pyramids before. There is this place in the desert where there are basically like test pyramids. There were like some hundreds of them. Where they are, and it was a scaling thing, right? It was a scaling thing. You see small little pyramids, medium pyramids, bigger pyramids. I don't remember the name of this place, but it was covered by the sand, etc. But eventually they discovered it and they understood they were trying to test the different approach. They were also used. They were putting some noble people there, etc. But we were also trying to build something bigger and bigger and bigger with time. And so they learned, that this shape of a pyramid was one of the best possible shape that you could use, and it was a big attempt, and they got it right. They got the right size, etc. So probably using some kind of rough scaling argument in the head, and it worked. I don't believe aliens help. I'm sorry, I don't believe in stuff like that until I have evidence. Whenever they present me with evidence, I will be the first one to say, "Whoa, this is amazing." It's I know against because it will be exciting. I just don't see the evidence right now. I'm interested in this UAP. They look interesting. They should be studied. I mean, I'm all for it. But until we have solid evidence that some alien race helped the Egyptians, we should go with the obvious, right? That they tried over and over again. They used some experience because people were very experienced at the time. They were some way more connected with the real world that we are right now because we spend a lot of time on the internet and we don't do things with our hands. We don't build, but at the time people did, and so they knew about stuff like this. But it's a beautiful argument. I'm glad that you brought it up because you can see that yeah, it makes sense, right? If you want to build something enormous like that, you want to have a lot of surface at the bottom and less mass as you go up. And you mentioned mountains that kind of have that shape, and there is a reason because again, it's not that somebody sculpted them beside the forces of nature. So if you have a big, how we think mountains are created is that when you have these, plates that are going against. It's almost like when you wrinkle a carpet, right? So you have these movements of the plates of the earth. They go against each other and they start to push the earth up. And then, of course, when that happens, you will have forces like the wind, water, etc. They start to erode this thing, and it starts to move stuff from the top going to the bottom. And over time, they take this kind of like a pyramid shape. And it's also a stable, because one of the things that also it's a principle in reality is what we call the uh, energy conservation or minimizing. Like whenever you have a system, you always try to minimize the energy that the system uses, right? So there is energy in the system due to gravity, etc. And so by having that shape, because gravity wants to pull down the mountain, it minimizes the energy in the system. It wants to keep always this minimum possible energy, and that is a shape that kind of it's a mini max kind of game. There are things that are trying to push down the mountain, things that are trying to push it up, and it tries to find the possible best solution that is this shape of the mountain. So that is a very great observation. I'm glad, because you start to connect the dots, things that you never thought of before. Now you're using this principle to come up with new ideas. So it's beautiful. Now there is actually a limit to how much a mountain can be, and in fact, it's all based on these arguments, because it's okay, how much force can you have, right? Because as we make the mountain bigger and bigger, you have more and more weight. Your gravity will pull down the mountain, and people you can use like normal physics kind of argument, but then people start to use also more sophisticated ones, like how strong repulsions you can have with atoms. So you kind of almost need to use quantum mechanics. This science studies things at a small level. That is kind of crazy, right? You're talking a big, huge mountain, but now it matters on the surface, because basically, if you're thinking about, even when we walk on the ground, we kind of never touch the ground. It's one of the things that my students, when they teach physics, find it so weird. We basically, the electrons in your feet are repelled by the electrons in the ground. And so it's a very, very small gap. You don't see it, right? It's a microscopic gap, but basically it's like magnets will repel each other. Does it make sense? This is why you don't go through stuff, right? Because the electrons in the atoms in your feet or in your chair, right? When you're sitting, right now I'm sitting here, my butt is not really touching the seat. It's like a little, they behave almost like little magnets, right? The electrons in my butt against the electrons in the chair, and they repel each other because they are equal charges, and you're kind of levitating. It doesn't look like that because you don't think about that, but you're kind of levitating above the chair, like very, very small little gap. Same thing with the mountain. The mountain is there, like kind of being repelled by the electron of the ground, right? It's not that, okay, it's not connected in the touch, but it's the same thing, right? And if that force that keeps the mountain up, due to the repulsion of electrons, gets broken because the gravity starts to be so much stronger, then the mountain will collapse in itself. So this is how it works, right? But that is at a really fundamental level. But you can think about maybe putting a bunch of billiard balls, right? Putting this billiard ball in a pile, and the pile becomes bigger and bigger and bigger and bigger. And then if maybe it takes one more ball, and then the entire thing collapses, right? So it's these kind of things that once you start to think about it, they really make sense. But this idea that we are dealing with different type of phenomena that relate to each other, like how mass grows with the cube, how the area grows with the square, and then they interact with each other, like in the pressure, and then you get these ratios that have to do with some kind of parameter that is scaling up. So with Bitcoin, for example, the number of people using the networks versus how many connections there are in the networks, how many people you can orange peel. All these are scaling arguments. This is why they come up in Bitcoin. I know it sounds weird because people want to think about Bitcoin like an asset, but we have all this evidence, and this is why we are doing these things where we think this is not a normal asset. It behaves like kind of like nature, like around us, with all these scaling properties. So this is why it's so important to understand these kind of things.
Yeah, and to your point, like a pyramid, it can't the volume can't or the mass can't go up by
Hmm.
the square because it's three dimensional.
Right.
It's got to be 2 point something. It might not be three, but at some
Yeah.
point that's going to overpower the 2 point whatever is going to overpower the square, and
Right.
then all
Exactly.
of a
So
sudden your
this is exactly
electrons
what
are
happened. So
getting crushed.
I don't know if anybody ever done a calculation of using the stones, because also we were using, I think we were using these limestones, right? We have a lot of limestones there. I think the pyramids are made of limestones that are relatively light, right? So, for example, if I used granite or some other uh, very heavy material, probably it could not even have been that big. Um, and so there is probably there's some calculation somewhere. Will be kind of cool to do it and say what could be the theoretical biggest possible pyramids that we could build with that kind of material, and I bet that probably the pyramids are kind of close to the theoretical limit of how they can be, and I can see how people think aliens did it because they are amazing, right? And imagine when they build it, they were really like people were like amazed, and like that we were covered by slabs of they did have marble or something that looked like that, but just on the cover, just on the surface. And, where we see all that gaps, all that little stairs, it was not like that. It was also smooth, and they took all that material because people use it to build other things, etc. They kind of this is what we did a lot. Even with the Colosseum, looks horrible like this. All it's beautiful, but it's a ruin, right? Because people were using it almost like a building like Home Depot. It was the ancient Home Depot. After the fall of the Roman Empire, people they wanted to build a church. They will go to the Colosseum and get statues or get marble or get something. They did the same thing with the pyramids. They took all this. Supposedly, we had like a gold little pyramid on top. Of course, we took that almost immediately after the Egyptian Empire fell. Um, and they took the marble, but it was a marvel. It was like incredible marvel. But the place was also different. I read somewhere that there are like little channels. They could use boat, to bring stuff there. But yeah, for sure, it was like an incredible um, feat, for humans using all these relatively primitive tools. Uh, and it's amazing, how big these blocks were. And one should be open. I don't think that alien did it. It was humans. Very clever, very smart humans, and they did it without formal science. They didn't have. They knew stuff. They knew a lot of stuff. They have these papyrus where they had formulas, for geometry, triangles. The Greeks took a lot from the Egyptian people, and in fact, where the word geometry comes from geo, that means earth. And one of the reasons why they developed geometric thinking was that the Nile was coming in and it was bringing all these silt, all these nutrients and all these good things, that were nourishing the ground because it was in the middle of the desert, and it has like cycles, like Bitcoin goes through these cycles where kind of inundate and floods everything, and it was bad because it's a flood, but also people liked it because it brought all these nutrients, that people then use for growing stuff. So we had all kind of rituals about that. We were celebrating it, but at the same time, if you have parameter that is scaling up. So with Bitcoin, for example, the number of people using the networks versus how many connections there are in the networks, uh, how many people you can orange peel. All these are scaling arguments. This is why they come up in Bitcoin. I know it sounds weird because people want to think about Bitcoin like an asset, but we have all this evidence, and this is why we are doing these things where we think this is not a normal asset. It behaves like kind of like nature, like around us, with all these scaling properties. So this is why it's so important to understand these kind of things.
Yeah, and to your point, like a pyramid, it can't the volume can't or the mass can't go up by
Hmm.
the square because it's three dimensional.
Right.
It's got to be 2 point something. It might not be three, but at some
Yeah.
point that's going to overpower the 2 point whatever is going to overpower the square, and
Right.
then all
Exactly.
of a
So
sudden your
this is exactly
electrons
what
are
happened. So
getting crushed.
I don't know if anybody ever done a calculation of using the stones, because also we were using, I think we were using these limestones, right? We have a lot of limestones there. I think the pyramid are made of limestones that are relatively light, right? So, for example, if I used granite or some other uh, very heavy material, probably it could not even have been that big. Um, and so there is probably there's some calculations somewhere. Will be kind of cool to do it and say what could be the theoretical biggest possible pyramids that we could build with that kind of material. And I bet that probably the pyramids are kind of close to the theoretical limit of how they can be. And I can see how people think aliens did it because they are amazing, right? And imagine when they would build it, they were really like people were like amazed, and that they were covered by slabs of they did have marble or something that looked like that, but just on the cover, just on the surface. And, where we see all that gaps, all that little stairs, it was not like that. It was also smooth, and they took all that material because people use it to build other things, etc. They kind of this is what we did a lot, even with the Colosseum. The Colosseum looks horrible like this. All it's beautiful, but it's a ruin, right? Because people were using it almost like a building like Home Depot. It was the ancient Home Depot. After the fall of the Roman Empire, people they wanted to build a church. They will go to the Colosseum and get statues or get marble or get something. They did the same thing with the pyramids. They took all this. Supposedly, we had like a gold little pyramid on top. Of course, they took that almost immediately after the Egyptian Empire fell. Um, and They took the marble, but it was a marvel. It was like incredible marvel. But the place was also different. I read somewhere that there are like little channels. They could use boat, to bring stuff there. But yeah, for sure, it was like an incredible um, feat, for humans using all these relatively primitive tools. Uh, and it's amazing, how big these blocks were. And one should be open. I don't think that they did it. It was humans, very clever, very smart humans, and they did it without formal science. They didn't have. They knew stuff. They knew a lot of stuff. We have these papyrus where they had formulas, for geometry, triangles. The Greeks took a lot from the Egyptian people, and in fact where the word geometry comes from geo, that means earth. And one of the reasons why they developed geometric thinking was that the Nile was coming in, and it was bringing all these silt, all these nutrients and all these good things, that were nourishing the ground because it was in the middle of the desert, and it has like cycles, like Bitcoin goes through these cycles where kind of inundate and floods everything, and it was bad because it's a flood, but also people liked it because it brought all these nutrients, that people then use for growing stuff. So we had all kind of rituals about it. We were celebrating it. But at the same time, if you had a plot of land and this was your land, you didn't know after the flood because even if you had markers or something, it will be destroyed by the flood. And so they developed this science of geometry, so they could calculate, say, okay, I can measure this from there, and I had this area, and this is mine place, this is your place, and so this is why it made sense to calculate these surfaces, these areas, etc. This is how it was developed. It was kind of all related to Earth, geometry, this the measurement of the Earth. So it was really cool. By practical things and practical needs, they develop all this knowledge. So yeah, very very cool stuff. Yep.
Yeah, that's
Okay,
cool. That's
so
really
let's
interesting. I like it.
finish